In this video, I'm going to give you an introduction using as many pictures as possible of the meaning of a component of a vector. When you hear this concept described in words, it seems very elaborate. So let's take a look. The first step should be the following. Imagine you have just a little arrow. So I'm going to draw an arrow on the paper. And the arrow will begin from this point, and let's say our little arrow extends to this point here. So this is a vector. Okay? And now we're going to examine the concept of a component of the vector. Well, first let's take a look at some purely geometric interpretations. So imagine you have the following. You have some sunlight coming down from here. Okay, so imagine these arrows represent sunlight. And they are hitting the arrow here, or what we are calling the vector in this context, as you see in the picture. And now the question is, what is the shadow that this arrow casts along the ground? Okay, so if you look carefully, the length of that shadow is from here to here. Okay, this is the shadow that the vector casts onto the ground down below. And say that this is the ground here, okay? So now you can also tell that there's an angle present here. Okay, we'll use the Greek letter theta to represent an angle, as is common in mathematics and in physics. So we have an arrow that's tilted this amount. Okay, it casts a shadow that you see here of blue length, right? The light is right above. And then you see that the length of the shadow here being cast onto the ground down below, this is what we could describe as the x component of the vector. So now we will call this the x-axis, and we could describe this as the x component of the vector. Okay, in other words, it's the length of the vector that lies parallel to the x-axis, or the shadow, if you like, that is cast onto the x-axis. So that's one step. Now the question is, how do we actually find the length of this shadow? Well, if the length of the vector from here to here, okay, say that length is given by L, then by basic trig, you can conclude that the length of the shadow being cast onto the ground is L cosine of the angle. And likewise, what you can say is something similar applies to the vertical part here, okay? So imagine instead now the following scenario. Imagine we have a y-axis, okay, as follows. And now, for some reason, imagine the light is coming from this direction. Then the length of the shadow cast onto the y-axis is this. Okay, so this is the vertical shadow. And once again, by basic trig, what you can conclude is the following, that this component of the vector is L sine theta. This is the angle, excuse me. This is the angle, this is the projection onto the x-axis, this is the projection of the vector onto the y-axis. That is L sine theta, this is L cosine theta. And L is the length of this arrow. Okay? Clearly you can tell that if you fix your L, okay, imagine that the L is fixed, and let me measure it so that I don't vary it in length. Okay, imagine that you fix your L at, and I will use centimeters, because that is the norm in sciences. Okay, imagine we fix the length of L here to be 7.5. Okay, 7.5. So what I will do is this. I will take my point here, and I will tilt the vector up. Okay, but I will not change its length, so it will still be 7.5 centimeters long. Okay, so I will simply tilt it without changing its length. So we'll still go from here to here as follows. Okay, so the length of this new one is the same as the old one. Okay, but now let's take a look at what's happened to the shadows being cast onto the ground and then onto the wall, so to speak. Okay? So now if you look carefully, the length of this shadow has changed. In fact, it has decreased if you compare against the one above. I think we're starting from the same distance here, you see? What's happened to the length of the vertical one, however? See, this one has correspondingly increased. Okay? So this is the angle now. The angle has gotten bigger. The length here has stayed the same. It's still L. This is still L cosine theta. This is still L sine theta. Let me label it L sine theta. Okay. We're imagining the light as before coming either from here to give us that shadow or from here to give us that shadow. So the key concept to understand is that the x component, if you like, the x component of the vector is L cosine theta, and the y component of the vector is L sine theta. The x component of the vector is L cosine theta. The y component of the vector is y equals L sine theta, as follows. So if we were to actually do this in one specific case, to illustrate the concept, let's take a look. This L is 7.5 centimeters. That angle roughly is 45 degrees. So 45 degrees. And we are going to find the component of the vector along the x and then the component of the vector along the y. So what we have is the following. X equals 7.5 times the cosine of 45 degrees. And for the y component of the vector, we will write y equals 7.5 times the sine of 45 degrees, as follows. Okay. So if I am a little person, imagine I can walk the following. What is the purpose of this? Imagine you're a little person, right? And you can climb up this vector here, and you can reach this point, okay? Or what you can do instead is this. You can go along the x component, stop over here, and then you can climb up straight this way, and the net result is that you still reach this point. Okay? So you can move along the x component, turn 90 degrees, and move up the y component to reach this point. Or you can climb directly along the vector and still reach that point. There you go. So this is a review of how you find components, what they represent, what they allow you to do, and hopefully a kind of mental model to build up your understanding in terms of little projections if you have light and shadows, so to speak. So thank you for watching.